Okay, Assalamualaikum and good afternoon, everyone. So, the idea of this talk is essentially to what you call introduce some things which I was not able to teach you while I was working with EPM. So let me put this in full view, I suppose. So essentially, one of the things, I think one of the significant things that has not been taught to UPM students at least, I'm not sure if you have been to other courses, then you might have seen some of this before, is to consider quantum field theory. And then before quantum field theory, that is essentially the beginning step, which is to incorporate relativity in quantum mechanics. How should I do this? I have to escape this because I don't have auto admit. Okay. So let me go back to this. So essentially, what we do is try to give some concepts leading to quantum field theory, but I will not be doing too much details. So let me just go to the content. So basically, what I'm going to do is to go into some preliminaries. Okay, basically some motivation as well, and then go to the usually the first thing that people look at is the Klein-Gordon equation and then the Dirac equation. And then we'll discuss some issues with respect to the solutions found for both equations. So, well, okay, this is very general introduction. So you have the idea of the two pillars of modern physics. I do not know whether we still need to call it modern because this is 20th. Well, it's been there from last century. So, so we have quantum physics and relativity. Most of us sort of treat the two subjects differently, but ideally one should have the two subjects sort of married together to form a relativistic quantum mechanics. But let's look back at what we have actually learned in quantum mechanics. We have the key equation here. I'm ignoring some other things. Okay, the key equation, which is the dynamical equation in quantum theory, is the Schrödinger equation. And if you write down the Schrödinger equation, which is the time-dependent one, not the eigen equation. Okay, so the time-dependent equation. Can you see my mouse, by the way? Somebody?
Yes, Doctor.
Okay, great. So the time-dependent equation is essentially have the time derivative here just to show that states will evolve according to this equation. And this equation applies to all quantum states. Okay, it's not just the eigenstates. The one that you have probably seen, the time-independent one, is essentially for eigenstates. So here is a general equation for any quantum state. Okay, and immediately we see if one expand what the Hamiltonian is. Usually we think of something from a conservative system. Okay, so you have the kinetic energy here, and then you have the potential energy here. Okay, so and you'll find that okay, the kinetic term will give you a second order derivative in space, whereas for the time derivative it's first order. So the order of differential operator is not the same. So definitely this is not quite what one has in relativistic theory, because in relativistic theory you have both space and time to be on equal footing. So this is not on equal footing. And then the other thing, okay, let me just admit somebody there. So the other thing was the usual wave equation usually has second order time derivative. And with second order time derivative, you will see later on there will be problems, essentially the problems with negative energy solutions. So so this is in some way, okay, if you go to relativistic form, there you are expected to face certain problems, okay? So again, the key thing is to make sure that everything becomes relativistic. Okay, so you need to build a different equation using some relativistic equations that we find in, say, special relativity. So I'm not going to touch anything on general relativity. Okay, so this is just flat space. And so the other uh, the other important thing that one should also have what you call consider is the idea of scales. These are normally not really emphasized in many places, but in one book, I find this is very nice. That Robinette, I'm not sure whether you have seen Robinette's book. They actually discuss in the first chapter to talk about when do you really apply relativistic ideas or non-relativistic ideas, uh, classical ideas as opposed to quantum ideas. So let me just go briefly through these ideas of scales. So for free relativistic particle, you probably have learned through special relativity that you have these relations of energy and momenta given by that, where the energy uh, contains both the rest mass energy, okay, and the kinetic energy. So the kinetic energy is actually given by the difference between the rest mass energy and the relativistic energy. So so what is the gamma, by the way? Gamma is just your ordinary relativistic factor. So over here, the idea of when do you go to realistic notion and when do you uh, not go to a relativistic notion is quite simple, because the idea is just to consider the particle's velocity here, for example, whether it's comparable to the speed of light. Okay, so in the case of a non-relativistic cases, you would want to have the ratio between the velocity of the particle to be much less than the speed of light. And then you can almost immediately see that your T becomes, well, you can expand your gamma here, and then you can actually reduce your T to a term which is probably recognizable as your kinetic energy. And your P is just your ordinary MV, okay? Besides looking at the idea of comparison of the velocities over here, sometimes it's also good to have considered the relativistic energy, okay, and then compare this to the case of where it's supposed to be non-relativistic. So the limit over here is given by this part of the energy, relativistic energy p squared c squared should be very much less than your m squared c4, which is essentially the contribution from the rest mass energy. So in other words, usually when you consider non-relativistic case, you sort of ignore your rest mass energy. And this is quite useful in a way because you can actually now, instead of comparing the velocity, which can be variable, okay, your v can be variable, you can actually, oops, sorry, you can actually just compare some estimates of your kinetic energy. Okay, given kinetic energy there, and then here's an example which is mentioned in Robinette. Is about the inertial electrons. I think I've missed one point. What's the ionization energy of hydrogen? I think it's 1.36. Anyone? Okay. Anyway, okay. So,
6.
pardon?
13.6. I think 13.6.
13.6. Yeah, that's right. Sorry. So I missed the 3 there. So you have the inertial electrons to have this much energy, where your Z will be your, what do you call that? Can't remember the atomic number or mass number. I think it's the atomic number, right? Yeah, Z. Yeah, Z is the atomic number, because I can't remember all the symbols. So over here, once you go beyond 46, for example, then your T calculated here will be, going beyond the rest mass energy. Okay, so in other words, for heavier atoms, the inner electrons are going to be relativistic. So there, instead of comparing speed, sometimes you do not know how to estimate the speed, but you can actually estimate the energy. So then you can actually consider, okay, this is going to be relativistic. Okay. So let's go to the other case. So this is relativity. So the other cases would be the quantum case, and the quantum case is actually difficult. Okay. First of all, quantum theory is actually characterized by the Planck constant. Okay. And the usual belief, even Dirac mentioned this, and then people raise the question, how do you actually compare this? That quantum theory has a classical limit, but how do you do the limits? Okay, so this is not obvious. So if you want to do the same way of comparing, like the case of relativity, where you compare the velocity of a particle with the velocity of light, okay, then you should look at what is this Planck constant supposed to represent. Okay, so the Planck constant actually has the same dimension of action or angular momentum. So if you want to make the same kind of process with respect to the case of relativity, then you should compare that. But this is unless you are doing some kind like Feynman path integral or something like that, where you actually consider your exponential of the path and things like that. I'm not going to go into that. So you just, unless you do that kind of thing, it's a bit difficult for you to imagine how you want to take this limit. Okay. And then the other thing, it also sets the scale for the Heisenberg uncertainty principle. Okay. So you probably remember that your delta X delta P should be greater than H bar. So in other words, this is one of the popular notion, is to think that one cannot have a precise trajectory in that sense, where your trajectory gets blurred in a way. Okay. So, but the usual way we think of how to look at whether it's quantum or non-quantum, and I say non-quantum, I mean classical here. So you normally use the concept of de Broglie wavelength. Okay. And one can actually compare the de Broglie wavelength of, say, a particle, okay, in comparison with the system being considered. Okay, this could be two things: the system being the object itself, the particle itself, or the system for which it interacts. So when it interacts with, say, an array of atoms, then you can actually some diffraction pattern. So the classical limit is when your, I have to get this right. Yeah, your classical limit occurs when the de Broglie wavelength is actually much less than the system typical size. So this is not really as satisfactory because it seems no, it seems to be depending on the size of a system rather than uh, the case of the relativity where you actually compare with some universal constants, which is speed of light. So, okay.
Sorry, can I
Yeah,
interrupt?
go
When
ahead.
you say compare depends size of system, meaning what? Meaning
Well, again, it's in the book of Robinet, it talks about two different system to consider is the size of the particle itself. So you can start to think whether, okay, can you treat your particle as a billiard ball kind of thing? So it's a classical particle, or you do need to consider the extended properties of the particle, which is the wave property. Okay. Or you can consider, say, the particle is going through certain interaction with some diffraction grating, for example. Then you will look at the size of the intervals of the diffraction grating, whether it's considered very large or not.
oh, okay.
So and this kind of so as I said, this is not as what you call elegant as the one with the relativity, because here you're not comparing with some fundamental constant. Okay, so but nevertheless, I mean, it's the kind of intuition that we get. Okay, when do you want to consider just some classical ideas, and when do you want to consider just you must consider quantum ideas. So the other thing that one can do with this is the idea of thermal ensemble. So you consider what you call a collection of particles distributed to some temperature. Then you can also see the way we do things is just to look at the thermal de Broglie wavelength. Okay? So you can treat the system to be classical if it obeys the same kind of thing. Okay. The other thing probably Dirac probably have actually what you call alluded to this idea in his paper here. Well, okay, this is the book here. He alluded that okay, there is a classical limit, but he did not quite show how. Okay, it's perhaps through the idea of the Ehrenfest theorem. So you get these mathematical structures. Okay, because if you look at Dirac's idea is to look at the mathematical structures in, for instance, in the D algebra, for example. Okay, so here you have the Ehrenfest theorem saying that okay, on average, your quantum observables tend to behave sort of similar to the classical laws. Okay, but again, it's not like the case of the relativity. So, in fact, there's a paper that I think is quite good to read, which is written by Klein here, that talks about how this idea one should take it step by step. So, going from a deterministic theory to a probabilistic theory, and then from the probabilistic theory, then you can make the connection to quantum theory, because quantum theory is probabilistic. Okay, so there are stages to be set. Okay. So so before we jump into relativistic quantum mechanics, we need to establish some what I call conventions that's been used. If if you've been in one of my classes for special relativity, I mentioned about the different conventions that people use. Relativists would start to use a certain kind of metric signature, which is a plus, 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 minus. Over here, particle physicists tend to use a plus, minus, minus. So I'm referring to a Walter Griner's book, which he's an particle physicist or theoretical physicist in high energy physics. Okay? So we adopt the plus is actually referring to the time component, and minus, minus, minus will be the spatial components. So you label your vectors here. Here's a position 4 vector, contrary 4 vector. It will be identified with your normal, this will be the time. Of course, you have by right, you should have the same dimension. So you multiply with C over here, and then your 1, 2, 3 will be your X, Y, Z. And because of the different signatures that you have for each component, you will find that your contravariant vector and your covariant vector is actually different. Okay, so you get for your covariant vector, you have a minus sign for your 1, 2, 3 components. And then you can also define it for other physical 4 vectors that you have actually come across. The other important one would be your momenta. So P mu, the 0 component will be related to energy, and then the 1, 2, 3 components will be your components of ordinary momenta. Over here, I mentioned how to get from a contravariant vector to a covariant vector using your Minkowski metric. Okay, so the Minkowski metric would be it will look like this as a matrix, and over here you can also get your inverse metric. So in the language of relativity, this is a covariant tensor, this is a contravariant tensor, and this is essentially inverse to this metric. And you find that you multiply these two matrices together, you get the identity. Okay, by the way, I'm abusing a little bit of notation here because your X mu is supposed to be components. I'm representing together with the whole matrix. Okay. So what else one needs for this is, okay, the idea of inner product. So again, just like if you think of your cats and bras, so you take a cat vector and then you multiply your bra vector, then you get essentially an inner product, okay, which is a generalization of your dot product essentially. And over here you get the squared length of position 4 vector. So you get your, essentially what you have seen. You probably have seen this in a different form. You have a differential instead, dx mu. Then this will be c squared dt squared minus dx squared minus dy squared minus dz squared. And that gives you the absolute 4 interval squared. Okay. All right. Then let me introduce also this, the inner product of 4 momentum. Okay, I'm missing a subscript here. So again, it's the same way, you contract the contravariant vector with a covariant vector. So in this case, you have contravariant vector for P1 and you contract with covariant vector P2. And then you should be getting this thing. And if you let your P1 and P2 be same, then you'll be able to show this relativistic relation. Okay. What about inner product between position and momentum? That's also important because you'll see this factor again repeatedly in your description of wave propagation. So here you get x mu p mu to be just simply the thing that you find in the phase of a wave. Okay, so this will be E is coming from your P here, T will be your 0 component X, and then the the spatial components. Okay. Okay. Now we try to move into relativistic quantum mechanics. So what do we do? Well, we begin, as I said, we have to begin with something which is known in relativity. So we begin with this one. Okay. So relativistic energy for your form momenta. Okay. And we start to give operator status to them. So, and but the assumption is that, okay, you need to reproduce it similar to the ones that you have seen in non-relativistic quantum mechanics. So in this case, we simply define P mu to be IH bar partial X mu. And you probably notice there's no negative sign here. It's because we already taken into account when you put this X mu over here. Sorry, let me just think. Yeah, do it right. Yeah, I might get mixed up with the P mu at the bottom, I think. So but essentially we'll be able to take care of the negative IH bar ddx that you have seen in quantum mechanics. Okay, so I might be using a different vector here. Okay, anyway, so yeah, that's right. Sorry, this is, if you use X mu over here, yeah. So to get P mu, the contravariant vector for P here, okay, so the mu is index on top, I should have your X mu here, which is the index at the bottom on the denominator. And that will give you, remember, that will give you, the one before, that will give you the minus sign. And that, okay, I just slip up on that denominator thing. Okay. And then you get the same thing that you have seen in non-relativistic quantum mechanics. Okay, so I'm just assuming that operator status for P mu, and then simply plug this thing into the relativistic equation over here, and then you know, with a little bit of rearranging, remember that this becomes an operator. It has to act on a wave function, and with some rearranging, you'll get this particular form, which you can see that this is really your wave equation. Okay? And this wave equation is known as the Klein-Gordon equation. Okay? And for the simplest case, one can, considering this is actually a for freely propagating solution, then you have your plane wave kind of solution over here. And the plane wave solution, you see again that kind of phase relation that we had before using the inner product. And over here, there's it's silent on the spin, and in fact, it should be no spin, okay, because we are not considering spin variables at all. Okay, so this is actually representing a spin zero particle. Okay, so what's the problem with this? Okay, first, there are, again, I think I've alluded earlier, we have this idea of negative energy solutions that might be a problem. So if you try to, let me go back. So you try to plug it in, and then you think of your E to be your eigenvalues, then there's, given that this is actually a quadratic relation, then one should not just consider the positive root, square root, you should also consider the negative square root. one of the things that we believe in quantum theory, whether it's true or not, is the principle of democracy. Okay, all solutions are actually realizable, so you need to consider both. Okay, so the only problem with this is, something which is negative energy is actually considered problematic in terms of particle theories, because that means there's no ground state. So in other words, if you think of it as a closed system, a particle can just simply falls down to a much more stable in a way. So in other words, it goes to negative energy states. Okay, so that is not good for a good particle theory. Okay? So one needs to be able to resolve this issue at some point. Okay? The other thing is probably of less, well, it's not, I mean, the earlier physicists actually thought about it, is to think about what about the probabilistic interpretation, and then you require there will be a probability current, and probability current will entail also the form in a relativistic version, which is a four current. So here's a four current. So in other words, what you have, if it's the spatial coordinates, then this will be your gradient, which is what you see in probability current in non-relativistic version. For relativistic version, then you also have the time derivative. Okay, it's not so much about the derivatives over here, okay, but what does J mu represent? So if J mu represents for the spatial part to be the current, probability current, then J naught will be your probability density. Okay. But then you see that just plugging in mu equals 0, you have something which is not positive definitely. So there's a problem of understanding this probability density for the relativistic version. Okay. However, this can actually be resolved in some way. So the resolution is to not consider probability density, but you have to consider what we call the charge density. So in other words, we look to some, well, in this way, it's actually like a special case. Previously, we don't talk about electric charge. Here you introduce electric charge. But then when you introduce electric charge, you actually introduce what you call other degrees of freedom. Okay, so one of the things that we need to do, for example, from special relativity, since you have a charge, you have a source. So if you have a source, then you have some electromagnetic field to be considered together. So your energy, for example, would be replaced by this difference between the original energy minus the electrostatic energy. Okay? And then your momentum will be replaced by something which is related to the vector potential. Okay? And in relativity, we know that both of these potential, your scalar potential and vector potential, forms a four vector. And that's great. So in other words, one can incorporate this into the operator status of P mu. But because of this incorporation of your sources, your potentials here, okay, one has to modify your derivatives, which is associated to the earlier P, okay, with another derivative, which is called a covariant derivative. Okay. So here I can ramble a little bit longer if I want to, but no, we keep it simple. This can be related to fiber bundles and blah blah blah, or in terms of gauge theories and things like that. Okay, but let's keep this simple. So there, what happens over here? You have to replace your Klein-Gordon equation that we had earlier. Which one was that? Yeah, this one. Okay, so you have the derivatives over here. So I didn't put the covariant form. Okay. So you would have, instead of just the derivatives, then you have the covariant derivatives. Okay. So over here, once you do this, it takes care of your zero component, because now we have a different interpretation coming in. We have instead of just simply probability density, we have a probabilistic charge density, and charge can be negative. Okay? And besides that, it also makes because of that possible flip of the sign of charge, you also find that you have instead of just one solution psi, you can also have your psi star to be a solution which incorporates the negative charge solutions. So that's how roughly how it resolves this probability density problem. Okay.
But I have questions.
Okay, go ahead.
This might be silly, but for the case of this replacement of the energy E, why we always have to minus the scalar potentials and the original minus what?
F equals to minus del
Minus.
V, right?
So it's nothing related to the having an electric charge less than zero, right? We follow the force, right?
Here there's a okay. I haven't checked this, but no, that is how should I say? You have to stick to one convention. So that is a flexibility, whether how you want to define your potential, for example. Why is it F equals to minus del V?
Yes, correct.
Okay? But here you always assume that, okay, the way we define it is to take a test charge from negative infinity to the source, as an example. Okay, so there you have the negative sign. You might have bring the test charge from a different direction, for example. Okay, but I'm not going to go into that. Okay. Right. So it's really a convention, but you have to be consistent.
All right.
Okay.
And one more thing for this probabilistic charge density is like current density.
So you have current density, but
so our standard. Do you have like H bar or did I miss it somewhere? Do you take dimensionless or you don't anything or the reduced Planck constant in it?
I'm not sure whether I've assumed that. I think it's here.
Oh, okay. All right. Thank you.
So, Doctor, I want to ask something about the probability charge density. So, what's the physical meaning of that? So, means that the probability to find a charge at
okay. So, in other words, if it's negative, then the charge is negative, but the probability density is positive. You know what I mean? So, it's the sticking into you stick your probability density with the possibility of positive and negative charges.
Okay.
Okay, so this is not quite as neat as you can go much more rigorous, I suppose, but it's a way to resolve this issue. For the other issue, which is mentioned before, which is the negative energy solutions, we have to wait to the very end, because then it will be a sequel to other things. Okay, right. Okay. So one of the problems that we know from here is that we are going from the case when you have the non-relativistic Schrodinger equation, things become simple because it's first order in the time derivative. Okay, and remember your time derivative is related to the energy, right? So when it goes to the second order, then then things become complicated because you have to consider negative energy. Okay, so one of the things that Dirac was trying to do is why not make it as first order derivative, time derivative. So he actually, this is not the okay. The way that I'm presenting here is probably the opposite of what happens in history. Okay, but we'll get to that. Okay, so here's the Dirac equation. Okay, the Dirac equation is given by linear terms and the derivatives. So this is a space-time derivative here. Okay, and then of course you need your mass for massive particles. Okay, and we try to interpret what kind of solutions that we have for this. Okay, now one of the things that would be useful is actually, okay, can you get from Dirac equation to an equation which is similar to the Klein-Gordon equation? Okay. In Klein-Gordon equation, you have your derivatives being contracted, but here your contraction of your derivatives with respect to some unknown matrices, which is actually called the Dirac matrices from today's literature. Okay, so what one does is try to multiply this equation with this factor, and then you will be able to get something which is almost similar to the case of the Klein-Gordon equation. Okay, so you get the double derivatives over here, and then you have your m squared. Okay, but it's not quite the same because you have this gammas sticking over here. But if one imposes this particular condition, okay, remember here your gammas are contracting on different derivatives. Okay, here's partial mu, here's partial mu. So if one says that, okay, this contraction of your gammas with this pair of derivatives should be equals to the contracted derivatives, then it will actually reproduce the actual Klein-Gordon equation. And that kind of condition is actually the condition that we have for the Dirac matrices, which people are now quite quite well versed in this idea. So and this condition is given by this Poisson. It's not Poisson bracket. It's called the anti-commutator. Sorry, anti-commutator of your matrices will be related to your metric, Minkowski metric. And people even have tried to generalize this kind of algebra to different dimensions, and they call this as the Clifford algebra. Okay. So, okay, what is this condition supposed to say? Well, it says that, okay, the squares of your zero gamma matrix is going to be the identity, and then the spatial part will be -1, and then it anti-commutes. And because of the anti-commutation, you'll find that your gamma matrices should be traceless. So that sort of limits what kind of metrics this Dirac matrix is supposed to obey. How am I doing with time? Okay, almost done. Okay, so now, given that, do I want to say anything else? Yeah, I should also say that it's obvious that one needs is essentially a 4x4 matrix. That's a minimum dimension of the matrix. If you try it with a simpler one, okay, then you will find that, okay, some of the constraints cannot be obeyed, okay, or becomes degenerate. Okay, so let's now look at the problematic issue in the case of relativistic quantum mechanics. So what one does is to look at the simplest case, again, the free particle solution. Okay, so write down the equation for that. Okay, and the free particle solution, we can actually use the form that we had from the Klein-Gordon equation, because it's just going to be a propagating wave. Where's that? This one. Okay. So this is just a plane wave. Okay. So you just simply substitute that into your equation, and it will give you this particular equation over here, which is quite simple to look at. The only problem is you do not know precisely what gamma mu precisely, but you can actually work it out. Okay. One of the things that we do as assignment questions is to work out the details of these Dirac matrices. Okay, but never mind. At least we know these identities that we have over here. Okay. So what one can do with this equation for this free particle, okay, is to multiply with gamma naught. So what happens over there? Remember, gamma naught is multiplying with this gamma mu. So if mu is actually not over here, then this will P naught, and P naught is actually related to the energy. And gamma naught square from the one before is going to be equals 1. So then you get an expression for energy. Okay. And then you have the rest, you know. So your gamma naught will be multiplied with your gamma, and then we dotted with your spatial components of mu here. And then since we multiply gamma naught throughout, so you also multiply gamma naught to m. Now, apparently, this is the form that this at least historically they play around with. Okay, they start because they start with the problem of how to define the operator version of your energy operator. Okay, so they start with that particular form, and this particular form can be written in terms of alpha and beta here. Okay? And alpha and beta can be worked out to be given by this matrix. Alpha is related to your polymetrics over here. So here is actually a 2 by 2 here, 2 by 2 here. So the whole thing is actually 4 by 4. Okay, and beta is just simply equals to, is the identity with the minus identity at the bottom. So, and they are Hermitian, because why? You need this to be, the whole thing to be Hermitian. Okay. So that's, yes? Somebody is asking question? Okay, maybe not.
Sorry, Prof. Maybe just a quick question.
Okay.
So if you just multiply by gamma naught, how do you get positive in E? I mean, you multiply the first equation with gamma naught, right?
Okay.
So how do you get the gamma naught m to be positive?
Gamma naught?
M. So because the first equation is minus m.
You bring out to the other part of the equation, the other side.
Oh, okay. Thank you.
All right. Okay. Right. Let me go back. So, okay. Let's try to find a solution for this. In this even simpler case where the particle is at rest. And you can, I'm actually, okay, by the way, I'm actually following Sakurai and what's the other author name? Napolitano, okay? So there's nothing new here. So you can actually solve it, and then you find that the independent solutions of the Dirac equation for the case of P equals to naught is simply related to the basis matrices for 4 by 4, 4 by 1, sorry. Okay. The only difference over here is again your exponential. So the first part, the first half is corresponding to the positive energy solutions. Second half is going to be the negative energy solutions. So this is convenient because essentially this is the simplest thing that you can get from the Dirac equation, and you get that sort of basis that you need. Okay, and then we try to do generalize the solution a little bit. Again, we are not generalizing in the most general sense. We take one of the momenta to be non-zero, and the rest of the momenta is zero. So here in this case is your z component. And then what's going to happen over here, you get your Dirac equation in this particular form. Okay, and over here, the only problem to get the solution that you need is the U1 until U4. Okay, the problem over here, this is actually non-diagonal, but you know how to do this. Okay, you diagonalize it, and you find the solutions, and the solutions can be given as this. Okay. There are physical interpretation for this, but I'm not going to go into that. But the first half is the positive energy solutions, which correspond to this plus over here. The bottom half is actually the negative energy solutions. So in other words, even with Dirac equation, it doesn't quite solve the negative energy solutions problem. So how do we go about resolving that? So Dirac actually invoked Pauli exclusion principle to consider, okay, essentially you have a sea of negative energy states which is being filled up. Okay, and being filled up, you don't actually observe them. But interactions with this particular sea, for example, a photon might interact with the state of the particle in that direct negative energy sea, and it will excite it. And it will excite that negative energy state to a positive energy state, and it leaves a hole. So this is the same kind of picture that one has when you talk about the NP semiconductor thing. Okay? So one considers the hole as a particle with the opposite charge with the same mass. And that is now known as the antiparticle. Okay. So that's basically I mean, there are details into these ideas, but conceptually, that's what's been used. Okay, the idea of holes being identified to be your antiparticles. Okay, but that tells us something else. Okay, that tells us you require this massive states in the negative energy sea, which also tells us that, okay, you're not just talking about a single particle. Okay, your solution that you have is really a solution that involves many other particles. Okay, and in order to do this, the appropriate formalism for this is actually quantum field theory. Okay. But okay, it might not be as neat as you might want to think, but Dirac equation also solve other things. For example, Dirac equation automatically incorporates Fermi-Dirac statistics, and there are some spin quantities that seems to be unexplainable in the non-relativistic context, but you can actually explain this in terms of the Dirac equation. So that is probably my last slide, I think. Yeah, this is my last slide. Yeah. So that's all that I can present for today. I know this is not so detailed, but no, I hope we get the ideas. Later on, we will probably go into some basic ideas of quantum field theory. Okay. Questions before we start the recording? Or you prefer to start the recording now? No questions?
So when do we usually use Schrodinger equation and when do we use the Dirac equation?
That's the thing that you might, I'm not sure, did you miss the first 2 slides or 3 slides? That we
Is
talk
it
about scale.
during the massive particle? Is it?
Yeah, we have to introduce some kind of scales where you want to consider the non-relativistic case and where do you want to consider relativistic case. Nothing, it's not automatic. So you have to actually, you have to remember that these are models to solve equations of the system. Okay, so again, so there is a flexibility of how to model things, and then you feel that non-relativistic is actually enough, then you just go for non-relativistic. But sometimes with respect to the quantum case, it can be quite a problem because you have this spin observable which is not really explainable in the non-relativistic case. Now, if you look at some of the new theories in the condensed matter, it uses a lot of Dirac equation.
Oh, yes, correct.
If, for example, if let's say Dirac equation is the more sophisticated one, producing sort of like better results. So why do we still want to use Schrodinger equation in this case? I mean, I understand the idea of scales, but
Why do we want to use Schrodinger equation? Because Schrodinger equation is simpler.
okay.
There are cases that you don't need to consider all the complicated things about the Dirac equation. By the way, okay, the Dirac equations are meant for those particles with which are fermions. The Fermi-Dirac statistic, the inclusion of Pauli exclusion principle is there. I guess.
Oh, no, okay. Yes, now I see. So everything's more involved electrons and everything. So they're all fermions. So Dirac equation is more.
Yeah. You remember the other thing that we had was to include charges. Okay, and then the coupling to some potential, which is your gauge field. Okay, so these are actually important things.
So Doctor, this might be out of range. How about bosonic kind of particles? Do we have any like more applications with bosons? But photon is the only, thing.
Okay, well, you have equations, covariant equations for spin 1 particles and covariant equations, but it will be no, you have to treat it separately. Because one thing about going to the relativistic, one of the things that I always try to introduce if I were talk about quantum field theory is this the idea of representation of Poincare group. Okay, with representation of Poincare group, you essentially cover all possible spectrum of particles. Okay, any other questions? Otherwise, I'll stop the recording first, I suppose. Maybe then you're less shy to ask questions. I'll stop recording.